Alright, here's a quick part 3 video for lesson 10.3.3. We're going to make it quick here. So the last part I left off on would have been part D, and it says how could you generalize the conjecture from part B, written as permutations and combinations, without really even realizing it. That's what I did down here, and so I'm not going to redo it. It's, again, just reinforcing here that idea that we could do permutations divided by the decisions factorial that will give me my combinations, or if we wanted to work kind of opposite of that, we could do combinations times the decisions factorial and get our permutations, and we're going to apply that in the last problem. So what we have is in one state, so this is a good problem because it's going to make us choose whether it's going to be permutations or combinations. We have to kind of read it and take the context of it. So it says, in one state lottery, there are 56 numbers from which a player can choose 6. Does the order in which the numbers are chosen matter? And for part A, the answer is no. The order doesn't matter. You could choose any of those 6 numbers out of those 56. And so the fact that order doesn't matter tells me that this is going to be a combination problem, which leads into part B really nicely. And it says find the number of possible combinations for a set of 6 winning lottery numbers. All right, so in part B, what we have is we're going to have 6 winning lottery numbers. Decisions don't, or I mean, sorry, the order doesn't matter. And what we have is we have my n, or my number of choices, is going to be 56 because there's 56 numbers to choose from, and they have to fill 6 slots. And so my number of decisions, my r, is going to be 6. And I shouldn't use the word decisions because we're not really making decisions here. I should really say like my groups, my choices and my groups, because there are there's going to be a group of 6 here that we need to fit these 56 numbers into. And so we have an n, we have an r. I could use my calculator, but I'm going to use that equation from back here. All right. So what I'm going to do is, if I can find it, I'm going to find the number of permutations, and I'm going to divide it by my decisions factorial, and I'm going to be able to find my number of combinations here. Sorry. And so what I have is I have 6 decisions being made. So my permutations look like this. It looks like 56 times 55 times 54 times 53 times 52. What am I at? 1, 2, make it 1, 2, 3, 4, 5. So I got one more. Times 51. Because that's my 6 there. 1, 2, 3, 4, 5, 6. That's my 6 for my permutation. Now I'm going to divide those 6 by my decisions factorial, so 6 factorial. Now what that turns into is 56 times 55 times 54 times 53. That turns into, down here, I get 6 times 5 times 4 times 3 times 2 times 1. Now this just becomes calculator work. And so I'm going to do it on my calculator here. And I'm going to do it all as one. So I'm going to put in parentheses. In parentheses, I'm going to put 56 times 55 times 54 times 53 times 52 times 51. Close my parentheses. And then I'm going to divide that set of parentheses by another set of parentheses. 6 times 5 times 4 times 3 times 2 times 1. Close that parentheses. And what I get is, for this lottery, there are 32,468,436 different combinations here. So there are a ton of different ways that these lottery numbers could be, lottery balls could be pulled. And then we have the last question here. What is the probability of selecting the 6 winning numbers? Well, out of all those combinations, there's only one right combination. There's only one winning combination out of those numbers. And so if we're talking about the probability, and I'm going to call it prob, you have 1 out of 32,468,436 chance of winning that lottery right there. Because there's only one right answer out of that total sample space of total combinations. All right, and we did a problem like that earlier where the numbers could repeat. This is a situation where the numbers can't repeat and the order doesn't matter, and so it became a combinations problem. That is the last problem. If you want to try 36 or 138, you can. Take a look at the math notes here today, and make sure that you take a look, if you want to, at the ebook and click on some of these definitions and see the definitions of where they're coming from. Other than that, if you have questions about permutations, making arrangements, how we can go from permutation combination or from one vice versa, please email me.